just maybe some keywords,
Yes,
not full sentences.
I will try. Yesterday we ran two cases for robust production and robust process. Some basic
We
principles
looked at some cases.
about
As the pendulum gets long, no matter what kind of variation you have during manufacturing in cutting the pendulum, your eyes won't be able to see much difference in the period of the pendulum, and that's what we call robustness in a narrow sense. And also we discussed the greenhouse case, and in that case, what was the problem? We were trying to produce some humidity in the greenhouse, and the humidity would be at 20% level, right? And compared to steam 1, the water 1 combination, we found steam 2, water 2 combination, suppose if we produce same 20% humidity, we found which combination more robust? S1, W1 combination, because it, even though we by mistake blow a little more or less steam than we want, and a little less or more water is sprayed, still we would be very close to 20% humidity inside the greenhouse. So those were the examples we discussed. And also we did a little bit of probability and statistics review for those who are not very comfortable with probability and statistics. Any questions before we start from yesterday? Okay. So in general, when we say robust design, we're talking about a product or a process, or in general a system to be designed. And there are some factors which we call control factors. Those are controllable by the designer. And there are also some other factors which we call noise factors, because they are uncontrollable by the designer, such as the oven type the customer will be using in making the cake. It's uncontrollable by the designer. And there are some outputs of the system. Sometimes we call them responses of the system, product process, and sometimes we call them quality characteristics if you would like to design high quality products and processes. And typically they are multiple in number. Multiple meaning Y1 could be the taste of the cake, Y2 could be the texture of the cake. And typically it is multi-response system. And further than the responses, as an analyst, we would like to convert these responses into some summary figures, and which we were going to call these figures performance measures. For example, the average taste, average texture, means of YIs we can take. We may also want to concentrate on the variances. So if you remember the pendulum example, and let's say this is the length of the pendulum, real length of the pendulum that we cut in our production, and this is the average length that we cut over all items that we produce. Remember, this was showing us sort of a frequency. Actually, we called it the probability density function, and it's a bell-shaped one. You remember this from your grades. Grades are also distributed like that, maybe not symmetric all the time, but some are less than the average, some are more than the average, and same thing goes for the pendulum length. Some pendulum parts are going to be less than the average, and some are going to be more than the average. So if we make an experiment with a process, let's say pendulum cutting process, and we increase the speed of the conveyor, decrease the speed of the conveyor, make some adjustments on the machine. These are under our control, and see if we can get very robust lengths, meaning we have the target length, say it is 50 centimeters long, but with very small variability. That's robust process, meaning it has small variability, and no matter what happens in the cutting process, the conveyors get old or not, and the human error, operators make errors or not, still you have many of the pendulums cut very, very close to this average. This is a robust process, and if we see we are robust enough, we may want to look at the average of the parts that we produce. This is what we mean by mean of yi's. Take yi as the length, and average of parts is just estimating the population mean, which is the true average of all the parts that we ever produce. And that is a performance measure to us. We're going to look at that measure, I from 1 to n, if we just take by randomly n pendulums from our production line, divided by n, that is going to give us some idea about where the center of our production process is. Is it more than 50? Is it less than 50? So it's pretty good performance measure, how good we are doing. And also we may want to take another performance measure to look at in these type of studies, which is S square, which is, remember, the sample variance. And it is like we take every part, look at the distance of the part from the mean, and take a square and take a sum, and divide this whole sum by n minus 1. This is also a good, very good summary measure or performance measure. So with these two measures only, y bar and s square, we can tell a lot about our process. Even if we don't see this graph, we can tell that, say, if this is close to 50, we can tell ourselves that we're doing a very good job. On the average, this is our target and we're keeping that. And if this is as small as possible, s square, if this is small, close to 0, we can tell to ourselves, we do a good job here. And therefore, many times in doing response optimization, multi-response optimization, we will not be using the responses as they are, but we will be using the performance measures of those responses. So, can anybody tell me what is the best thing to do with these performance measures? For the pendulum example, as a manager of this whole process, what would you like to do with the mean? I actually already told you this, but I want to hear this from you. What should be the mean? Let's say I'm telling you about the mean, and what do you want with the mean? Yes, to be at 50. You want the mean to be bar. Typically we use bar to show that it's an average. We want the mean to be at 50, ideal. So, what do you want to do with the s squared?
To be as low as possible.
Yes, we want to minimize it. Minimize it. Have you started taking linear optimization programming course? Yes?
Yes.
Okay, have you started writing linear programming problems, formulas or formulation of those problems? Have you started? Okay. What's a linear programming problem? What does that look like? Can anybody tell me?
A collection of linear inequalities and equalities?
Yes. Do you say minimize a function f of x subject to, which is a linear function, subject to some constraints like ax equals b? Did you start learning that?
Yes.
A little bit? Okay, so typically, if I were to write an optimization model, could anybody write an optimization model on the board using these requirements? Can you put this into an optimization format? Optimization, mathematical programming model format? Okay. So, maybe you have not gone very far in linear programming course. That's okay. I can write this problem. This is a problem. I have two objectives. This is my first objective, goal, and this is my second objective. And mathematically, I can express this like, my problem here is to do the following. I want to minimize the distance between average of my production, average of all pendulums cut, the length of the pendulums cut, minus 50, maybe absolute value of that. I don't care whether it is more or it is less. Do I care? I only care that it should be, and this is called a multi-objective optimization problem. It is the language we use to tell some other people how we see the problem. So as long as I manage achieving these two objectives, meaning have very, very small variability in my production system, make S squared as small as possible, and also as long as I have the average mean of this process at the target, I will be happy. And solve this problem subject to these conditions, meaning conveyor belt speed should be within acceptable boundaries and all the other parameters should be within acceptable boundaries. In linear programming, there is a little difference from this kind of formulation. First of all, you have only one objective. And secondly, what? So I'm testing your linear programming background. And these, let's say you don't have this objective, you have only this one perhaps, or that one. And this objective is a linear function of x's. So maybe I can express this as a function of x's. I will show you how later on. And maybe I can also express this as a function of x's. I can also, I will also show you how to express such a performance measure in terms of all the controllable variables. Unless you express these in terms of x's, you would not be able to problem is not necessarily a linear programming problem. Typically, in multi-response optimization, our models as F1, F2, they are nonlinear. And typically, we don't have only one single objective, but we have more objectives at hand. So that makes multi-objective optimization a complicated problem. Take linear programming. It's complicated on its own, but of course there are very well-established procedures to solve such problems. But unfortunately, when we have more than one objective, and we have nonlinear form of the model's objectives and the constraints, the problem becomes a bit more complicated. But we will learn easier ways first, and then we will learn more advanced ways, hopefully, throughout this course. So performance measures are very, very important for us because we will be building models for them, and we will be trying to find optimal values of them. Any questions so far? Anybody in the class who has not seen such a formulation before? Okay, good, and that's fine. But this is the language we will be using from now on to express our desires and our problem at hand. Okay, let me concentrate now, before we do the exercise using Minitab, let me concentrate on a very good performance measure which we call loss, quality loss, or consumer loss. And that measure is a combination of these two measures. Because when we have two objectives at hand, life becomes complicated for us. Solving that problem becomes difficult. For somehow, if we can find a way of combining them into a single objective, that would be great. Do you have any suggestions of combining these two into a single objective? You know that you want to minimize S square, and you know that you want to minimize y bar minus 50. So if I tell you, you have only one chance of telling me about an objective, what would you tell me? In English, forget about the mathematics. You would say, I want to minimize S square, which is the variance, and you would use the logical operator and before you finish the sentence, I want to minimize the distance between y bar and 50. Would you say so? Minimize S square and computer guys like this and y bar and the difference between y bar and 50. This and typically is what operator?
Logical.
Division, addition, multiplication?
Addition.
Addition. So if I say instead of and, if I sum these two things, does it serve my purpose? Like, if I'm allowed to combine these two into a single objective, would it make sense try to minimize this whole thing altogether, like S square and y bar minus 50 altogether? Is it logical? So you are looking like I don't buy this. Huh? Is it okay?
Yes.
Yes, okay, good. Different cultures cultures have different expressions. You know, when you ask an Indian guy, a guy from India, is it okay? He says he does this. What do you understand?
Smile.
Yes.
You need.
Yes, but in for example, Turkey, this means no. No, I don't like it. I don't want that. Yes is this one. So what's yes in Ukrainian? Same? Yes. No. So we agree with each other. Anybody who has a different gesture for yes and no?
I think Bulgaria does.
Bulgarians?
I
Bulgar?
think so.
You think we have we have a person from Bulgaria. Juliana, what's the gesture for yes? Yes, it's the same.
Bulgaria? No.
Bulgaria.
Yeah,
Okay, good. So we want to combine s squared with y bar minus 50. Yes.
I have a question.
Sure.
Why is and addition? As I know that and is multiplication usually.
Okay, well, I was asking you and you said
Addition
is
is
okay.
or is addition.
Okay. So you're suggesting we can multiply?
Yeah, I guess.
But when we multiply, this becomes nonlinear.
Yeah.
But when we add, this is linear, life is easier for us. That's one explanation. Okay, well, look at this one. This is absolute value. Instead of absolute value, what else I could use? I don't want minuses and pluses cancel each other, by the way. I want to penalize being away from the target no matter what the true value is.
make square and get a root.
Yes, I can make a square here, if I like. And this square and that square seems very comparable. That's also nice. These are all intuitive things. But let's give more meaning to this kind of a phrase and see what that means actually. Let's look at this graph. And it's like our pendulum leg distribution. And if I were to plot another function on top of this one, this is the probability density function. And let's say that function is lost to me, to you, to the society, to the manufacturer. It's the discomfort, it's the money lost. If I produce a pendulum right at the target, I assume I'm going to have no loss because everything is perfect. Is it okay? Let's say there is a pendulum in my hand which is a bit far away from 50 centimeters. And this is not working as much as I desire it to work, right? So it's going to occur some loss to me. Let's imagine it's not hryvnias, but it's some discomfort because it's a bit longer. A quadratic loss function. This is nothing but the average loss to me, to the society, to the manufacturer. So it's not bad to sum these two things up. And you were saying, why don't we multiply? Who were saying, why don't we multiply? Were you saying we should multiply?
Yeah.
Can you tell me now, addition, does it make sense? It does. Why? Because if I add s squared to y bar minus t square, its logical interpretation is?
Yeah, but it's still not linear, as you said. We want to keep it linear.
Well, maybe it's not linear, but it has now it has a nice explanation, which is the average loss to the society. Okay? Because assuming a quadratically increasing loss to me as I get away from the target, this represents average loss to the society, which I want to minimize, right? So that's good. That kind of adding two objectives to each other is good. Yes.
I'm just wondering that I understood why there is a misunderstanding. If we talk about logic operators or and there is multiplication and so it's different. And now it's not the same logic.
It's not
we
the
need-
same logic.
Yeah, we just need to make not to combine our objectives and make one objective, and we may do it in this way.
Yeah, we can sum it, we can multiply it, and yeah, usually we take n as a multiplication. But here, if you sum it, it has a good meaning, which is the loss to the society. And that's we can maybe choose and we try to minimize that thing. But of course, when you try to minimize this whole thing, you give maybe, what kind of weight do you give to these things? S squared is as important as y bar minus t squared, right? So these are sort of equally weighted. Okay? And none of them is more important than the other. But there are other ways of combining the objectives, and we will be discussing those. But this is a nice explanation, assuming quadratic loss to the society. And Gunichi Taguchi, he was a Japanese researcher. He was originally an electrical engineer. He just showed us several years ago, late 1970s, he showed us that if we think in terms of these directions, like as we produce products away from their target values, we incur loss. Maybe not for accounting purposes, not in terms of money, but we actually incur some discomfort, some in general loss to the society. And the way we decrease this loss is by decreasing these two things. One of them, on the average, we have to produce at the target, but that's not enough. We have to reduce variability in our production system. And that's therefore attracted our attention to the idea of robustness. Before Gunichi Taguchi, we actually in production manufacturing systems, we did not care much about this S word. We did not care. And we all cared on the average we produce target products. So he was the person helping us realize that problem. Any questions, comments? And as B increases, of course, loss per deviation may increase. So for different B's, you may have different loss functions. When you visit industry, you have hard time explaining this to industry people. Do you know why? Because they have in their mind this goalpost problem, what we call goalpost problem. Remember our tolerances, lower spec limit and upper spec limit. What was that, remember? We would tolerate 49 centimeters as low as 49 and as high as 51 centimeters length. We would tolerate that because we're not perfect. So these guys are telling us, Professor, why are you bothered with this variation? As long as we produce items within these limits, everything is okay, isn't it so? As long as you produce items within limits. So why are we creating this problem to us? To come to Kiev and teach it? Imagine you are the customer. I'm going to give you 2 distributions. This is a TV set resolution. Monitor or your computer's resolution. And you want ideally the resolution to be a certain number of pixels per area, and it cannot go as low as this limit. It shouldn't go as high as this limit. I don't know what happens if it goes very high. Maybe it burns your eyes. I don't know. TV resolution. Pixels per unit area. This is a real story. We're in year 1972. You were not here. And Asahi newspaper published these graphs in Japan. This TV was produced in, this was Sony TV, produced in the United States. These TV sets, again Sony, produced in Japan. People were buying, preferring Japanese TV sets. I remember this from my childhood. People were saying, buy from Japanese, not American. Okay. And the Asahi newspaper was trying to explain why this thing is happening. The newspaper, look, do you have such newspapers? We don't have them in Turkey, but maybe. Saying that, look, the distribution of the TV sets resolution is like this in the United States, Sony plant. And in the Japanese Sony plant, it's like that. That's the reason why people are preferring Japanese TV sets. Can you see why?
They are more stable.
Because they minimize the S value.
Yeah, well, and the newspaper was going on and saying, look, average loss to the society for the Japanese TV sets is less. But for the US TV sets is more, because S square of this distribution is more than this distribution. As a customer, do we check S square when you buy something? What is the S square of this bottle? Water. You don't know. You never care. But you drink it. What is the variability for this one? Taste. Now I think I've been drinking it for 3 days now. It's the same taste. Good. But if this bottle had a different taste, I would say, this company produces different taste. I'm not going to buy it. I'm going to buy this one. This is the same taste. So that's what I care. I don't check their S square. I don't care. But I can feel it. They can feel it. So the resolution, if you buy Japanese TV set, resolution is close to target for all products. Imagine you buy an American at that time, Sony TV set, and it is very, very close to the upper limit or very, very close to the lower limit. What is the chance of purchasing a TV set very probability that the resolution is going to be less than A and more than lower spec limit, because all of these plants are checking resolution of each TV set. They're not selling these items to their customers. They're making sure they are selling items within the tolerances, no problem. But if I buy Japanese, then the chance I will be getting a TV set with resolution A or less is just that little thing, little area. Here, it is that area. It's small but bigger than this one. How many of you say A? B? C? D? Any D's? Okay, the correct answer is C, because expected loss is variance plus the bias from the mean squared. There's no bias, but variance is 16, so it should be a multiple of 16. Clear?
Why there is no
Because in the question it says this process produces parts on target on the average. This process produces on the average at the target. So there's no difference. All right. Okay, simple exercise. We have another performance measure, similar, very similar to loss function that we use in optimization. Because again, combining the two objectives makes life easy for us, which is called signal to noise ratio. Anybody who heard of signal to noise ratio before? Typically electrical engineers use this term, signal to noise ratio. And it's in decibels. And remember Taguchi, he was an electrical engineer too. So he found an analogy between electrical engineering field signal to noise ratio and these functions, and he developed this signal to noise ratio. So there are actually three types of problems we're dealing with: smaller the better, larger the better, and target is the best. These type of problems that I have been mentioning, these are target the best type of problems. Like TV resolution, there's a target. Shouldn't be any smaller, shouldn't be any larger. All the other TV sets resolutions. Pendulums, it's a target the best type of a problem. But some problems are smaller the better is the case. For example, gas energy consumption. Smaller the consumption, the better it is. The loss function looks like, again, a quadratic function, but you don't have the other part. And you can express loss to the society as a constant, a coefficient, times y squared. So as the gas energy consumption increases, loss increases quadratically as the square of the energy and gas consumption. And this is the average loss to the society. It looks like this formula. If you plug in, instead of the target 0, you get s squared plus y bar squared. So it's the average loss to the society. And Taguchi proposes to use a very similar figure to optimize, to maximize actually, which is y bar squared plus s squared. You take a logarithm and multiply it by 10, that converts it to a decibel scale, and you put a minus there because Taguchi wanted a small rule for the industry people to memorize. Signal to noise ratios are always maximized. Therefore, he put a minus in the front. If you maximize which is 0 practically, and then y bar square gets a minimum value which is 0 practically again. So minus 10 log y bar square plus s square is the kind of measure we're going to use from now on in our optimization. And we will see other advantages of taking a logarithm. Taking a logarithm will help us in our analysis. And minus is for maximization. So we convert this minimization problem to a maximization problem by putting a minus in the front. Questions here? Clear? And similarly, we can define a performance measure to maximize by using larger the better type of problems. Here, loss function for larger the better problems is in this form. Let's assume it is so. For example, larger the strength, the better it is. Larger the mechanical power, the better it is. Larger the wear-out resistance, the better it is. And in that case, you can represent loss to the society as the items get smaller, the loss gets bigger, as a constant times 1 over y squared. So loss is proportional, inversely proportional to y squared. And if you take an average of such losses, you will get this figure. It's a bit strange. It doesn't look like this one, but it makes sense. If you want to minimize this loss, you need to minimize s squared here because it's in the nominator, and you need to maximize y bar squares because they are in the denominator. So this function gets a small value when s squared gets a small value, and then y bar squared gets a high value. So that's what we're looking for actually. We want to minimize s squared but maximize this response. And signal to noise ratio is just a function of loss to the society. What you do is you just take a logarithm, that's it, multiply it by minus 10 for maximization reasons. Because you want to minimize this one, and to maximize you put a minus, and you take a look for other reasons I'll tell you about later. Questions about these loss functions and these performance measures called SNR, signal to noise ratio? Make sense? Okay, but there could be other combinations. This is only one way of combining it using an analogy with loss functions, loss to the society. And this is the case we had been discussing. Nominal is the best. Sometimes we call the target value the nominal value. Do you know the English meaning of the word nominal? What does that mean? Economists may tell us. Nominal.
It's a planned value.
Planned supposedly should be this value. Supposed value. Nominal is the best. So this is the loss, and in this case we have two loss functions, two signal to noise ratios. One of them is minus 10 log s squared, that's just to minimize this s squared. And then the other one is 10 log n y bar squared, that's to maximize, to bring the mean to target. But these loss functions, use of them are a bit different than the previous loss functions. Here again, you have two objectives, which we don't like. But the previous two cases are easy. With only one single objective, if we find solutions that maximize this or minimize this, that's going to be the robust design we're looking for. Let's let's look at an example here. And before we start with the example, I'm assuming you have no questions. Okay. Let me briefly look at multi-response optimization approaches. I just mentioned one way of formulating the problems, another way of formulating the problems. But typically, like for a design optimizer starts with data collection. We do start with an experimentation at various different levels of, let's say, cake recipes, pendulum production process, and greenhouse humidity production process. So we do experimentation. We collect some data. And we fit some functions to this data using regression or using ANOVA, analysis of variance. We analyze variability in the data by some graphs, and we may build empirical models that relate part product process characteristics to signal-to-noise ratios, to performance measures, to loss functions, to responses, whatever we want to use. We may use regression analysis, we may use analysis of variance, or we may use just simple graphs and just see what is going on with the data, and then we try to find optimal values of these controllable variables. We can directly use the response data in optimization, or directly use performance measures, or we can use the surfaces, the empirical models. So first we are going to be looking at the case of direct use of the data because it's easier. Then we will be looking at the other cases of using empirical models, functions. Questions about this? Let's look at direct use of response data. And here we are going to be using Taguchi methods. Taguchi was an engineer, and he wanted to help industry people. And industry people do not want complicated things, do not like complicated formulations and analysis and solutions. So he wanted to simplify the life for them, and so he just developed some graphical tools. And those tools, of course, they rely on data collected. This is a very typical experimentation format that we suggest using. The blue part shows us the combinations of levels of control factors. And the green part, the yellow part shows us the noise factor combinations if we can. And the green part is the data collected under noise, under control conditions. So we basically end up repeating each control factor combination several times. Could you please look at your cookie worksheet 1 in your computers? Everybody has cookie worksheet 1?
So guys, you need a computer, you can like...
Do you need a
take seat at
computer?
your place.
Yeah, 2 of you can work together, no problem. 2 of you can work together. Two of you can work together. Do you have your own? Yes. Do you have Minitab with you? Oh, see? This is what? Oh, I see. It's a laptop. Good. I thought it was an iPad. Things are getting tinier and little, and I don't know what's gonna happen. They say we're gonna roll them.
Yeah.
We're going to roll them and put it under our arm and carry.
It's a
That's the technology.
Flexible screen.
Flexible screen.
Yeah.
That's opti-electronics. Where opti-electronics?
Here, over there.
Are you in my class?
I am the operator.
Okay. So you're my Good. A requirement for being an operator is to attend the class. Did you know that? No, I'm just kidding. Okay, good. All right. So we're all fixed. Let me introduce our problem. The data comes from this problem. Do you like these kind of cookies? Do you have these cookies in Ukraine? Here.
Yes.
These are American cookies, typically. Very soft. Supposed to be very soft and chewy, like a cake. Sometimes they're called cake cookies. In Turkey, they're at least called cake. Anyway, so chewiness is a very important customer requirement. Why? Why? It typically shows a response, TV resolution, chewiness of the cake or cookie. That's our requirement. What are our other requirements, responses of the cookies that we make? Sweetness, taste, the look, and so on. But let's forget about all the others. Just concentrate on chewiness. And how do you measure chewiness? Do you know how? You just eat it.
Experiment.
It's chewy, very chewy, hard. Well, let's say we are not doing that because we don't like that kind of subjective data in our optimization. Let's say we are measuring chewiness by using physics. Anybody who can help us with chewiness measurement using physics? Let's say this is my cookie. So I apply a force on the cookie and measure the newtons until it breaks into 2 parts. So that's my chewiness measurement.
Mechanical test.
Mechanical test. Now, you don't need to eat it because you may get fat throughout this process. Okay, so we measure chewiness. Is chewiness larger the better, smaller the better, nominal the best type of a response?
Smaller.
Chewiness, smaller the better. You apply a force. If the chew is very tough, with a little force it breaks into 2 parts, so we don't want that. It should be chewy, so you should apply a lot of force to squeeze it, okay? So it's kind of larger the better type of a problem.
But if you can, if it's too,
It's like liquid,
It's like a
of
gum.
course. Well, let's assume it's larger the better as the chewiness figures, as the amount of force you apply on the cookie increases, it becomes more chewy, more chewy. Let's say it's larger, the better type of a problem. Now, what is our purpose? See, many of my examples come from the kitchen because I'm a woman instructor. No, these are very famous textbook examples. These cookies, I want to develop a recipe so that these cookies are as chewy as possible, so maximize chewiness, and I would like to have robustness in the sense, no matter where the cookie is, like on the side of the tray or in the middle, they should be equally chewy. Typically sides burn and middle is more chewy. I don't want that. And another thing, so that's the cookie position, which is my #1 noise factor. And another thing, when you take these cookies out of the oven, they are fresh chewy. But if they wait in the room temperature for some time, they become hard. And I don't want that either. So even I test these chewiness of the cookies at a low temperature, which is when they cool down, they should be chewy. And even if I taste them right after, when they are right after the oven, they should be chewy. So whatever the temperature, test temperature is, they have to be chewy. And no matter where the cookie is placed, they have to be chewy. So that's my two noise factors. And I claim I can develop a recipe so that I guarantee these two things. We'll see. Maybe I can, maybe I cannot. So we'll see that. And what are my control factors? I am the cooker, so I can control the cooking temperature. I can adjust the oven temperature myself to a low temperature, say 150 degrees centigrade, and to a high temperature, say 190. So let's pick these two levels in my experimentation. I don't need to experiment with a lot of levels. That's the good idea about it. I don't need to do that. And syrup content, which is the amount of sugar. I will try a low and a high figure for the sugar. And for the cooking time, I will try short and long. What happens when you keep things in the oven long? They become, yeah, they will become hard. So what if they are too short? They're not going to be cooked well. But I will try two reasonable small and large figures. And cooking pan. Somebody tells me that cooking pan may affect your results. It is a solid one like this, or it's a mashed one, a bit mashed pan. I may try these two things in my experiment. And shortening time, corn oil or coconut oil. These two things I will try. I am hoping that one combination, say low, high, short, solid corn, may produce real good results to me. If I want to see that, how many experiments do I need to make with these two combinations? How many experiments? Any idea? Take cooking temperature A. It can be low, it can be high. Take syrup content B. It can be low, it can be high. Go on like that. What happens?
120.
Minus, 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 plus. Minus is a low level, plus is a high level. So 2 times
7.
how many?
7. 5.
How many? 32. So I need to make 32 trays of cookies. A lot of experiments. Who's gonna eat all these things? And some of them are burned, some of them are not chewy, and all that. So Taguchi says you don't need to do the full design. This is called a full factorial design. Full factorial experimental design. And you don't need to do that. Even if you do the full design, there are temperatures that you have not tested. Smaller design. Can you see this design in your laptop? One shows a low level, 2 shows a high level. And certain combinations are there. From the 32 experiments, he has selected 8 experiments to do. Yellow part. But I'm not going to show it in here. The yellow part is somewhere here, which is in my mind. It is a full factorial design actually. And this is the data I have collected. Let me show you the yellow part on this presentation. So these are my Chwinist measurements, and the very first column corresponds to side-low combination, meaning I made a tray of cookies using 1-1-1-1 combination one time, meaning low, short, solid corn combination. One time I made these cookies. Then I randomly took a side cookie and waited 25 minutes in room temperature until it cools down and measured its chewiness. This is what it means. So I randomly closed my eyes, took this side cookie and waited 25 minutes and measured its chewiness. So it gives me an idea about how hard it is. Then, second time, I made another tray of cookies under the same 1-1-1-1-1 conditions. And this time, I randomly picked a side cookie but measured chewiness of that right away. Right away when it's very hot. And I yet made a third tray of cookies and measured randomly a middle cookie, room temperature, and finally the fourth tray of cookies, I measured the middle cookie at a very high temperature when it's right after the oven. So now I have 4 data, 4 observations. That tells me in real life what's going to happen if I use these selections for A first level, for B first level, and for all the others first level. And if I summarize this data into mean, look, take the average of 2, 6, 4, 8, mean is 5. So the average chewiness I'm going to observe in real life is going to be somewhere around 5. That gives me this mean information. And this standard deviation, 2.58199, that gives me square root of this thing, S squared. And I can also take a logarithm of that and calculate a signal to noise ratio. So these are the means calculated, and these are the standard deviations, these logarithm of them, and this final column is signal to noise ratio. And I calculated that by taking inverse of the squares first and then summing 4 figures and then taking an average, taking a log, multiplying it by 10. So Minitab does that automatically for us. Once I enter my data to Minitab, all I need to do is go to DOE, Taguchi. After, of course, I enter the data, the analysis menu is going to be apparent available to me, and I will be able to analyze my Taguchi design. So, and it's going to create these columns automatically in the analysis menu. This is how I first design my experiment, then collect my data, and then convert everything into some summary figures, like mean, like variance, like signal to noise ratio. Any questions?
So now we need only select situation, scenario that when our signal to noise will be the biggest one.
Yes. Well, now we are into the analysis. This is the data collection.
Yes.
Yes.
And what about Y1, Y2? How do you put these numbers like randomly?
No, no, no. You do the experiment literally. You get into the kitchen, cook the things, and do the force test. Measure it on the display. It says 5 newtons. You go here and write 5. You literally collect the data. But luckily, I give you the data. You don't need to, in this hot summer, you don't need to bake these things. So this is the real experimentation. Sometimes we don't do this experimentation physically, but we use computer simulators. Can you simulate the cookie baking process?
Not really.
Cars. Yes. Using differential equations and balance things. Very difficult. But in aviation, for example, you can simulate failures under stress modes and when the plane takeoffs and lands down, certain failures happen. You can simulate these things. If you can, you don't need to get into the kitchen or the lab, but many times you cannot. So you have to physically do these things. Okay, let me show you more of the analysis, and tomorrow you will do some exercises on your own. You just develop a response table and these graphs. And let me tell you a little bit about these graphs. These are called main effect plots. Again, the software is generating them for you for your analysis. And this is such a graph telling you what happens to the signal to noise ratio if you use the first level of factor A. Let me tell you how it is computed. Look at the A column. These very first four experiments assume first level of A. So you go to signal to noise ratio column, take an average of the first four. That's going to give you an idea what will happen if you set A to the first level on the average. And then similarly, you go to signal to noise ratio column, take an average of the second four. And that's going to give you an idea what will happen on the average when you set factor A to the second level. We agree? So, the computer software, Minitab, and many other software packages like SPSS, IBM Model Builder, Stat Graphics, name all the rest, they do these graphs. They tell you what's going to happen if you set factor A to first level and if you set factor A to second level. What do you see in here? If you want to maximize signal to noise ratio, remember we want to maximize signal to noise ratio, which level of A is more promising? One. And similarly, which level of B is promising? And if you go on like that, here you go, there is a recipe. It says that if you pick the first level of A and for the other factors, second levels, maybe you get the maximum signal to noise ratio, which is minimum variability in chewiness and maximum chewiness, supposedly. Did we test this combination 1, 2, 2, 2, 2? Let's check. Do you see 1, 2, 2, 2? But we have tested, like out of 32, 8 of them. And what are those? Here, what is the maximum signal to noise ratio? 30? Can you see? 30. So what is the recipe for that? 1, 2, 2, 1, 2. Oh, maybe we found a better recipe, which is 1, 2, 2, 2, 2. Because the analysis tells us so. Are you with me? How many of you are not with me? I'm lost. Who says I'm lost? I just started thinking about cookies and I'm lost. Huh? Are you hungry? Okay, it's about time to finish, but so the main effect diagram tells us there's a very promising recipe. If you pick 1, 2, 2, 2, 2, you're gonna get even better results. And what we need to do is we need to go and try these things. And if we try these things using the prediction menu, there is a model behind this analysis. And the model is a linear model, linear programming, linear model. So the model is very simple. This whole analysis is a very additive linear model. But if they are additive, so we can separately find optimal levels, like I find the optimal level of this independent of that, and also this independent of the others. If the life is like that, cookie life, then I should get a signal to noise ratio like 3507. And that corresponds to mean being 37, chewiness, and standard deviation being 5.89, which is even better than all the figures I have tested and obtained so far. Look at these figures. My mean is 37. The best I got 35. And standard deviation is 5 point something. Of course, you see lower standard deviation figures here. Why didn't I get a lower one? But I got a 5 here. Why?
Because in general, it's worse than our solution. We have two parts. One part is better, but the other one is.
Yeah, typically we have two objectives. One of them we want to maximize chewiness, and we want to minimize this standard deviation or variance. There's a compromise. Isn't life like a compromises? You are here, you cannot attend neuroscience class. So it's a compromise. And the chewiness got better, 37. Unfortunately, variability, there is some variability still in your results. So this is the compromise you had in maximizing signal to noise ratio. Because signal to noise ratio, this thing put more weight to chewiness on the average than standard deviation. Okay, questions?
I have one.
Yes.
If our parameters that we change in experiments, if they have some connection, if they are not separate, we can't do this. Yes?
No. That's called an interaction phenomena. And I can tell more about that tomorrow.